find our extreme value of f. Min max. Min and max. Oh. X, y, z equal 2x plus 2y plus 2z subject to the constraint x squared plus y squared plus z squared equal 9. Okay, I think it's going to be a little longer because this is a function in terms of x, y, z. Okay. Always set the one gradient vector is the multiple of another gradient vector. Okay, so it's going to be a fx equal lambda gx, fy equal lambda gy, fz equal lambda gz. Do a constraint equation here. And we also have a x squared plus y squared plus z squared equal 9. Okay. Fx is 2 equal lambda times 2x. 2 is equal to lambda times 2y. And then for this one, it's just 1 lambda times 2z. X equal 1 over lambda. Y is equal to 1 over lambda. Z is equal 1 over 2 lambda. Yeah. 1 over lambda square plus 1 over lambda square plus 1 over 2 lambda square equal 9. So what do we have here? We have a 1 over lambda square plus 1 over lambda square plus 1 over 4 lambda square equal 9. Well, you guys can do a common denominator here. And we have a 9 over 4 lambda square equal 9. From there, you see that 9 equal 9 times 4 lambda square. So lambda square is 1/4, meaning that lambda is plus or minus 1 over 2. It's to have two values. Okay, for each lambda, we get a point. Remember, each lambda is associated with the value of x, y, z. For lambda equal 1 over 2. x equal to 1 over 2. Y equal same thing. Z equal to 1. No. For lambda equal -1 over 2. So x equal to -2, y equal -2, z equal -1. Now sub each extreme point into fx, y, z. F 2, F -2, -2, -1. What's F 2, here? Yeah, 2x, 2y plus z. So okay, so we have a max and a min. That is it. This is the max, and this one is the min. Phi min max value of fxy equal to 2x squared plus 3y squared minus 4x minus 5 subject to the constraint x squared plus y squared less than or equal to 10. This is an inequality constraint, so you got to be careful. Right? It is not an equality constraint. Right? And there are two parts to this inequality. One part is the x squared plus y squared equals 10, and then the other part is the x squared plus y squared less than 10. We cannot apply the Lagrange method for less than. We can only apply the Lagrange method for constraint equality. For this one, if you cannot use the Lagrange method, then you got to use the method that is in the earlier section. Right? You got to figure out the critical point inside the region D. Set the gradient factor to the 0 factor to find all critical point inside the region. Find all critical points inside region on x squared plus y squared less than 10 inside the region. Okay, so set the gradient vector to 0. Fx equals 0. Fy is equal to 0. Okay, so fx is going to be 4x minus 4 equal to 0. Fy is going to be y set y equal to 0. Here come x equal 1, y equal to 0. So that means we'll have one point here. Okay, we finished step 1. Now we're going to be using the Lagrange method to take care of all the extreme points on the boundary. On the region okay, Lagrange method. The gradient vector of f is equal to some multiple of the gradient vector of g. We did it right down here. So for x minus 4 equal lambda times 2x. And on the other side, it's going to be set y equal lambda times 2y. Set y minus 2y lambda equals 0. Factor. 2y 3 minus lambda equal to 0. So we know that y equal to 0 and lambda equal 3. X squared equal 10, so x equal to plus or minus 4. That means you get poised here. 4, 0. Negative 4, 0. Two of them. For lambda equal 3. For x minus 4 equal 3 times 2x. For x minus 4 is 6x. So I mean well, negative 4 is minus 2x. Oh, it's 2x. So x equal negative 2. Reuse the constraint to get y. I'm gonna do constraint again. I'm gonna have to reuse constraint to equation x squared plus y squared equals 10. Okay, so sub x equal negative 2. I run out my color here. Okay, so minus 2 squared plus y squared equals 10. So y squared is 12 and y is going to be plus or minus root 12. So that's 2 root 3 poised minus 2 to root 3 minus 2 minus 2 root 3. So we have a total of 4 extreme points and 1 critical point. And then we're going to test them all out. Step 3. Evaluate each critical point and extreme point in step 1 and 2. 2. So let me write function here. Plus 3y squared. So 2. Actually, I'm just going to do 1 7. I'm going to write the answer to the other one at the same time. Right? Okay, so for the first time, everybody can see that it is going to be a -7. And yeah, I may have you do something like this on the exam. So let's have you try this one out, see if you're able to do it. Here come one. Sometimes I favor, short application. A box with open top, half surface area up. (12 square meter). Find its max volume. Four. Yeah, it's gonna be 4. Okay, so this is the open top here, right? Quickly get this thing now. Open top. Okay, it's the open top, so it's gonna be a x that y z. Yeah, if I set up x y z like this, that means we're gonna have to maximize volume is f x y z x y z. Oh man, it's gonna take you a while. Constraint. The constraint is gonna be we don't consider the top, right? So it's gonna be xy plus 2yz plus 2xz equal 12. Use Lagrange multiplier and you should be able to get the answer to be 4 cubic meter. So just a little help in for you guys, right? It's gonna be yeah. So when you do this thing, you're gonna get 3 of them, 3 lambda. And then here's gonna be a constraint equation. Well, for equation for unknown, you can do whatever you want. Eventually, you'll be able to solve for x, y, and z. So here you're gonna get lambda equals something, right? Here you're also going to get lambda equals something. And here you're also going to get lambda equal to something. You can set any two of them equal to each other. So if you set this equal to this, then you're going to set the other one equal to the other one. And then, you know, eventually you're going to figure it out. Huh? I'm going to call it lambda 1, lambda 2, lambda 3. Huh? You can set lambda 1 equal lambda 2. Right? Lambda 2 equal lambda 3. Or lambda 1 equal lambda 3. Oh, man. And then work it out. You're going to figure it out. Right? Example, find the point on the plane 1/2x plus 1/4y plus 1/4z equal 1 closest to the origin. Yeah, if you see something like this, then you can turn this into an objective function and a constraint equation. So here it is talking about distance. So distance to origin. Closest is the minimum, mean distance to origin. So we know distance to origin is d. Right? Is root away to origin, so it's x squared plus y squared plus z squared. Well, the thing here is that when you set up the objective function, so you're going to minimize. You are not going to minimize d though. You're going to minimize d squared, which is x squared plus y squared plus z squared, and this is your fxy here. Yeah, this is for the same reason that is in calculus 1. Right? You can do this because if 0 less than equal x less than equal y, then 0 is also less than equal x squared less than equal y squared. That is true. So better to do the d squared than to do the square root. And then the constraint is gonna be well, it's the plane itself. Okay, I'm gonna give you the answer here. The answer is well, 4/3, 2/3, 2/3. Okay, guys, have fun with these two problems.